Okay, well, we're still talking about symmetric positive definite matrices, the easy case as we discussed earlier. Let's add in another difficulty and see how this impacts things. So suppose we have some observation error, and this will look like y is equal to ax plus some e. It's an unknown error vector. In Rn. Well, one thing we could do, since we have a symmetric positive definite matrix, is we could just say that x tilde is equal to A inverse y, and as we've done before, but now this is going to be A inverse times Ax. Now we have our additional error term in here, as that's going to give us x plus A inverse times the error. So for this solution, our total error is x tilde minus x, guess I connect those vectors, equals A inverse times the error. Okay, let's suppose our error is really small. What is this going to look like? So let's take a blue. Well, so we already know that matrices or vectors are stretched or shrunk depending upon their respective eigenvalue makeup, if it's projected onto the basis of our eigenvalues. So let's start by looking at that. What is the largest eigenvalue of A inverse? And that's going to be 1 over lambda n, because according to our convention, lambda n is the smallest of the eigenvalues. So the error E could be amplified by as much as 1 over lambda n. So here's another question to think about. Is it possible that the error E is completely in the null space of A inverse? Well, the answer is no. In other words, there's no A inverse that's going to kill E, because for that to be the case, A inverse would have to have a minimum eigenvalue of 0. Well, if A inverse had a minimum eigenvalue of 0, that would mean that A had a maximum eigenvalue of infinity, which doesn't work. So we're always going to be stuck with some error, and there's nothing we can do about it. But we will find that there are things that we can do to keep everything under control. So let's say that we did have a large eigenvalue, or a very small eigenvalue in our original A, 10 to the minus fifth. Then the error could be multiplied by a large amount. By what? Factor of 100,000. So in our example, lambda, or sorry, the norm of this could be up to 100. So these values are arbitrary, and they don't really have units. They don't have anchoring in reality. But you can see how a small amount, a small eigenvalue in our original A can lead to huge amounts of error amplification. So, as another example, let's assume that A, and I mentioned this earlier, I'll go with a different color. Suppose A blurs the rows of an image. So you have some beautiful picture that you've tried to capture, but you were moving the camera when you took the picture. So in addition to that, there's some noise added from the sensor. So what we would have is y equal to ax plus e. We'll have our camera that's shaking. And I would say it's a cheap camera that adds pixel noise, but they all do, so we don't even have to do that. Pixel noise tends to be greater in low light than in high light, but this is the pixel error from the CMOS sensor. And X will be our image pixel row. Let's put it that way. So blurring has a low pass effect. So blurring is generally a low pass operation. So the frequency response that we might expect from this blurring on a particular row of the image might look something like this. So what does this have to do with the matrix A? Well, we'll get there in a minute. If we went back to our example when all we're doing is taking the Fourier transform of some filter and dividing it to get back to our original one to do deconvolution, the largest eigenvalue is going to be here, and the smallest is going to be here. And so A inverse would have to generally look like that. And it's going to amplify the noise a lot in that little area where we had cancellation by the blurring filter. So this amplifies noise. So one important finding relevant to this is that note, as the dimensionality increases, the smallest and largest eigenvalues tend toward the Fourier spectral and the max respectively. So we'll talk about that more later. But this is a good way to kind of tie your frequency domain intuition in with the what's going on with A. So in general, you can just think about it this way. If the A operation is going to cancel or minimize some signal dimensions, then A inverse is going to have to amplify those same dimensions a lot to get it back. And those correspond to the areas of minimum eigenvalues of A and maximum eigenvalues of A inverse correspondingly. And it has the potential to dramatically increase the noise.